So today we are going to discuss about how to find out limits of recurrence relation. What do you mean by a recurrence relation? A recurrence relation actually defines a sequence in which each term is related to its previous term. Right? This is what is called your recurrence relation. And nowadays, this recurrence relation becomes a hot cake for JEE Main and Advanced. And that's the reason why we should learn recurrence relation right now. So let's dive directly into our today's class. We will start our discussion by taking an example. You see, a recurrence relation is given to us where we have been said that an plus 1 is 1 over 4 to an plus 3. Here your n is all greater than equals to 1, and you should know that n belongs to natural number. And we all know that for any recurrence relation, we always be provided with some initial values. Here the initial value a1 is 1 given. Now from here we have to find out the limit n approaches to infinity an. Okay? Now you see, finding out the limits of recurrence relation, it's a huge thing. I mean, you have to understand different theorems to actually solve this kind of problem. But I can tell you we don't need all those theorems right now. The main theorem that we should know, one should know while solving recurrence relation is what called your monotonic convergent theorem. So this kind of theorems right now we don't need. Because in our JEE context, we will be only given linear recurrence relation. What is that? Linear recurrence relation. This will be given to us. And for linear recurrence relation with constant coefficients. Now, this relation which is given to us is basically a linear recurrence relation. Now, what is the other side of the coin? It is non-linear recurrence relation. Now, what is a non-linear recurrence relation? When you see that the term which defines the sequence is looped with the previous terms. Like, if I say an plus 1 is an into 1 minus an minus 1. This is a nonlinear recurrence relation. And I can assure you, nonlinear recurrence relation is not going to come in our JEE because in JEE syllabus it is not there. Is it clear? So we will be only given linear recurrence relation and we should know how to handle it. So now the first thing that you must check is whether the relation, I mean the recurrence relation which is given is monotonic or not. What do you mean by monotonicity? Whether the sequence is increasing or decreasing. This is the only condition that you have to check at this level. You simply check whether the sequence is increasing or decreasing. Okay? Then all you will say is your limit n approaches to infinity. You will take an, we have to find out this limit. We will say that this limit exists and we will assume that its value is L. Now, since it is converging to a value, the limiting value is converging to a point, so this will be same as your limit n tends to infinity a n minus 1, or it will be limit n tends to infinity a n plus 1, and so on. We will say all this limit exists and its value is L. Now we will learn how to find out L. Now remember one thing. In this kind of questions, as I told you, we will be always provided with some initial values of the sequence. You should see, after finding out the value of L, two things we should be concerned about. One, this L should not be below the lower limit which is given to us. In this case, we have been given A1 is 1. So we must be very sure that the value of L that we are getting should not fall below 1. This is number one. And number two, limit n tends to infinity a n, which is our L, this should not approaches to infinity. If this two thing happens, we will straight away say that the limit does not exist. Is it clear to all? Absolutely clear. So what you will do, whenever a recurrence relation is given, it is guaranteed you are going to get a linear recurrence relation. So all you will do is, you will simply check its monotonicity. Whether the sequence is increasing or decreasing. I will show you. I will take several examples to explain that. But remember that you have to check whether it is increasing or decreasing. The moment you get that, we will assume that this limit exists and its value is L. And we will find out the L. The method I will show you. You will find out the value of L. If you find that your L is falling below the lower limit given in our initial condition, or your L is approaching towards infinity, in both the cases we will say the limit does not exist. Otherwise, whatever value we are going to have is the value of this limit. Is it clear? Till this, is it clear? Okay, let us say this example. We are having a n plus 1. Let me change the color of the pen. We are having a n plus 1 is 1 over 4 to a n plus 3. Now, let me put n equals to 1. So, what you are getting? You are getting a2 is 1 over 4 to a1 plus 3. Why I am doing this? Because I have to check whether it is an increasing or decreasing sequence. So, you have to simply find out 2-3 values and you can predict whether it is increasing or decreasing. So, this thing is basically 1 over 4 to a1 is given to us as 1. So, it is coming to 5 over 4, which gives us 1.25. Next, let us put n is 2. So, we are actually having a3, which is your 1 over 4 to a2 plus 3. a2 we got as 5 over 4. So, 2 times a2 will be 5 over 2 plus 3. So, it is 11 over 8. So, this is coming like 1.30, so it will be 8 3s are 24, so it will be 60, 7 8s are 50. So it is almost like 1.37. Now I will calculate only one. Let me just put n is 3, so we are getting a4 is 1 over 4 to a3 plus 3, so that gives us 1 over 4 to a3. a3 is 11 over 8. Plus 3. So it comes like 1 over 4, 11 plus 12 divided by 4. So we are basically having 23 over 16, right? So it is coming like 1.96. So it will be 1.4 something. But that's all. No need to calculate more. Now you observe one thing. Whatever values we are getting, you see your A1 was 1, then it is 1.25, then it is 1.37, then it is 1.4. So it is what? It is increasing. I mean, the values are increasing. So this sequence is an increasing sequence. This is an increasing sequence. Right? So what I will do, we will simply say, let us say this limit exists and its value is L. Now, whatever recurrence relation we have been provided, all we will do is we will take limit on both sides. N plus 1, 2 times limit n tends to infinity n plus 3, right? Now, this is basically L, 1 by 4, 2L plus 3. So we are having 4L is 2L plus 3 implies 2L is 3 implies L is 3 by 2. Now what we have seen, that the limiting value is convergent. I mean the limit is convergent and it is converging to the value 3 by 2 and which is greater than 1. Right? So this limit, which limit? This limit exists and its value is 3 by 2. That's it. Nothing else. And we should not, we should not think more than this, at least at this stage, because we don't need it. We will be only provided with linear recurrence relation and we will simply approach the way I told you right now. Okay, let me take another example. See this question. Again, a recurrence relation is given. Xn is 2xn minus 1, 1 over n. And here your n is greater than equals to 2. And we have been given, n is obviously a natural number. And we have been given initial value, x1 is 1. So first I have to check whether it is increasing or decreasing. So let me just put, in place of n, let me put 2. So we are having 2x1 plus 1 over 1. I'm sorry, I'm putting 2, right? So it will be 2. So in this case, what we are getting? 2 into 1 plus half. So that gives us 5 over 2, which gives us 2.5. Okay? Now, let me put n equals to 3. So it is x3 equals to 2 times x2 plus 1 over 3. So that gives us 2 times 5 over 2 plus 1 over 3 gives us 5 plus 1 over 3. So it is 16 over 3. That gives us 5 point something, right? I don't need to calculate. We can easily see that it is an increasing sequence. So the sequence is increasing, right? The sequence is increasing. Let us assume that the limit exists. N tends to infinity. Xn, which is same as your limit x tends to infinity. Xn minus 1. Let us assume this value be L. So, we have been given the recurrence relation like this. Let me take limit on both sides. So, limit x approaches to infinity, xn is 2 times x tends to infinity, xn minus 1 plus limit n tends to infinity. This is not x tends to infinity, it's n tends to infinity, right? These are all n tends to infinity. So n tends to infinity 1 over n. So in this case, this is L, this is 2L, and this is 0. So from here we are getting L is 0. That is, the limiting value is converging to the value 0. But see one thing, it is below the lower boundary. The lower boundary is given, x1 is 1. But our limit is converging to the value 0. It means this limit, which limit? Limit n tends to infinity xn does not exist. As it is falling below the lower boundary of this sequence. So I will say that the limit does not exist. Is it clear to everyone? Let me take another example. So this question, here they have given a1 is root 2. a1 is root 2. And we have been given an plus 1 is equals to root over of an plus 2. Have you seen all the relation, all the recurrence relation are linear? So in this case, I will simply find out some initial values to check whether it is increasing or decreasing. So let me put n is equals to 1. So we are having a2 is root of a1 plus 2. That is, a1 is root 2. So it is coming like 2 plus root 2, right? Now, let me put n is 2. So we are having 3 plus 2. So it is coming like root over of 2 plus root 2 plus root 2. Now we can easily see one thing, that your a2 is greater than a1 as well as a3 is greater than a2, and this thing goes on. Means again this series, this sequence is an increasing sequence. Yes or no? Yes or no? Clear? Now, let us assume limit n tends to infinity, an exists and equals to L, which is same as your limit n tends to infinity, an plus 1. So, in the recurrence relation which have been given to us, let me take limit on both sides. So, limit n tends to infinity, an plus 1 is equals to limit n tends to infinity root an plus 2. So let me just replace this thing by L, which is equals to root over of L plus 2, square both sides. So it's coming like L square minus L minus 2 is 0. So if we factorize, we are going to have, so from here we are getting L as 2 and or L as minus 1. But L cannot be minus 1 because it is falling below the lower boundary. So this is rejected. Therefore, our L is 2. That is, the value of this limit is 2. And that's your answer. Is this clear to everyone? Absolutely. No doubt about it. Okay. Now let us take some other flavor of recurrence relation. Now in this question, they have not asked to find out limit n tends to infinity an directly. All they have given us is a recurrence relation like an minus 1 minus n is n by n plus 1. This is given to us, and we have to, and the initial values we have been given. In this case, your n is greater than equals to 1. N belongs to natural number. And the initial value is given, a0 is 2. And we have to find out the limit for this expression. That's it. Which expression? This expression. Okay? Now, in this case, what I will do, I can easily see that this sequence can be solved by telescopic method. This we can understand very clearly from this, because we only need an, that's it. So for that, what I'm doing a little manipulation in the numerator. I'm writing this n as n plus 1 minus 1 divided by n plus 1 factorial. So this can be written as n plus 1 over factorial n plus 1 minus 1 over factorial n plus 1. So which can be written like 1 over factorial n minus 1 over factorial n plus 1. Is it clear? Now, let us start putting values. N equals to starting from n equals to 1. So if I put n equals to 1, we are getting a0 minus a1 minus factorial 2. Then let me put n is 2. So a1 minus a2 is 1 over factorial 2 minus 1 over factorial 3. Now let us put n is 3. So we are getting a2 minus a3 equals to 1 over factorial 3 minus 1 over factorial 4. And this thing goes on. So the last term will be a n minus 1 minus an equals to 1 over factorial n minus 1 over factorial n plus 1. Now let me add the corresponding sides. If I add the corresponding sides, what you are going to have in the left hand side, these terms will get cancelled. So obviously this term will also get cancelled. And in the right hand side again, this term, these terms will get cancelled. So we will be left with, in the left hand side we will be left with a0 minus an is equals to 1 minus 1 over factorial n plus 1, right? a0, we have been provided the value 2. So n is 1 minus this thing. So your an is coming to 1 plus 1 over factorial n plus 1. Is it clear? Now we have to find out the value of log an. So let me take log on both sides. And there is a factorial n plus 1. So let me just multiply both sides with that. N plus 1 ln 1 plus 1 over n plus 1. Now let me take limit on both sides. Limit n tends to infinity. Which is coming like limit n tends to infinity. Factorial n plus 1 ln 1 plus 1 by ln n plus 1. Okay. Now we know a standard formula. The standard limit people all know that when limit x tends to 0, ln 1 plus x over x is 1. That is, when x is tending towards 0, this is tending towards 0. And the same thing is in the denominator, which is also tending towards 0. And the answer will give us to 1. So in this case, if we observe, we will find that when limit n is approaching towards infinity, this part is tending towards 0. So I need the same thing in the denominator. So what I will do, I will simply take this factorial n plus 1 in the denominator in this way, 1 over, factorial n plus 1 in the denominator. Is it clear? Now, as n is tending towards infinity, this is tending towards 0, and the same thing is in the denominator tending towards 0. Therefore, the value of this limit is 1. Have you understood this? Is it clear to everyone? So this is actually another flavor of recurrence relation. Okay, let's take another problem. So this question, we have been given a1 equals to 1. And we have been given an is an minus 1 plus 1. Now, Pn is given this expression. And we have to find out limit n tends to infinity, Pn. So, the right hand side of Pn, it has to be manipulated. It has to be related with the recurrence relation that we have been given. We have been given n is n. So let me just do one thing. Let me divide both sides by an minus 1. So this thing will give us an minus 1 plus 1 by an minus 1. So we can write in this way, an over an minus 1 is basically n into 1 plus 1 over an minus 1. Okay? And if you observe carefully, you will find that this part, it almost resembles this part of Pn. Isn't it so? If I put different values of n, we are going to get the right hand side of Pn from this recurrence relation. So let me start putting the values first. This recurrence relation is valid from n greater than equals to 2. So let me just first put n equals to 2. So we are having a2 over a1 is 2, 1 plus 1 over a1. Now let me put n equals to 3. So we are having a3 over a2 is 3, 1 plus 1 over a2. Then let me put n is 4. We are having a4 over a3 is 4 into 1 plus 1 over a3, right? And this thing goes on. So when we put n, we are having the last term will be n over an minus 1 is n into 1 plus 1 over a n minus 1, right? But we have to reach to 1 plus 1 by an. So I should not finish my sequence over here. Here we have put n equals to n. Now let me put n equals to n plus 1. So if I put n plus 1, we are going to have n plus 1 by an is equals to n plus 1 into 1 plus 1 over an. Okay? So now if I multiply the corresponding sides, what we are going to have? a4, a3, this thing goes on. an minus 1 into an plus 1 by an. And in the right hand side, we are getting 2 into 3 into 4 till n plus 1. And we are having 1 plus a1, 1 plus a2, 1 plus a3, and this thing goes on, 1 plus an, the last one, right? This is what? This is our factorial n plus 1. And what is this? This is our Pn. And in the left hand side, just check it, what we are going to have? This will get off, this will go off, this will go off, then this and this will also go off. So we are left in the left hand side, an plus 1 over a1 is equals to n plus 1 into Pn. And we all have a1 is 1. So we are having an plus 1 is basically factorial n plus 1 Pn. Is it clear to everyone? Yes or no? Okay. Now, what is Pn? Pn is basically an plus 1 divided by n plus 1. Okay. So this is what we got about Pn. What we got about Pn. Okay. So now we are having, actually we have been given, I am taking this very initial relation that has been given. It is n into an minus 1 plus 1. Okay. Now, what is your an plus 1? It is coming to n plus 1. In place of n, I am writing n plus 1. So it is an plus 1. Now, let me divide both sides by factorial n plus 1. So what we are having? An plus 1 divided by factorial n, because this can be written as n plus 1 into factorial n. So this and this will go off. So we are left with this. So this can be written as 1 over factorial n plus an over factorial n, right? So an plus 1 by factorial n plus 1. Let me write it here. Okay, let me write it here. So Pn is basically 1 over factorial n plus an over factorial n. Again, if we calculate, we can easily see we are having an is this. So what will be an over factorial n? This will be an minus 1 plus 1 divided by factorial n. So that gives us what? An minus 1 plus 1 divided by factorial n can be written as n into factorial n minus 1. So it is only n minus 1 factorial. So this can be written as what? N by factorial n can be written as 1 over n minus 1 plus an minus 1 over factorial n minus 1. And this thing will go on. So ultimately you see the denominator, the first was n, then it is n minus 1, then it is n minus 2. So a stage will come when this will be, and this thing will go on, a stage will come when it will be 1 over factorial 2 plus a2 by factorial 2. Now again, how you write a2? I'm writing it here. How you will write a2? Let me just write this one, or let me just copy this one. Otherwise, every time I have to write so much of thing. So we are actually having this thing. Right? So this A2 can be written as what? Again from this one, what you can write? This thing will go on. And this one will be 1 over factorial 1 plus A1 by factorial 1. Now A1 given is 1. So this A1 will be replaced by 1. So our Pn is coming to 1 over factorial n, 1 over factorial n minus 1, this thing goes on, 1 over factorial 2, 1 over factorial 1, and this thing is 1. So can you see this series? Can you understand what kind of series they have given? I'm writing it here. What kind of series is given when your n is tending towards infinity? When n is tending towards infinity, then this term will also tend towards infinity, right? And what is this series? This series is nothing but e to the power 1. Therefore, limit n tends to infinity Pn is nothing but e. That's it. And that's your answer. This sum is little bit critical, but you must understand this sum properly to do sums in the exam, even if some, difficulty is there in between. You can handle those kind of sums. If you can understand this sum, how I have related my recurrence relation with the given expression which is Pn. Is it clear? I hope now finding out limits in recurrence relation will be easy for you people. So let me give you one homework. This is the sum. This will be your homework. Please do this sum and definitely comment me its answer. So see you tomorrow. Till then, take a very good care of yourself. Thank you so much.